Yes.
Could you do number 10 on the practice test before we start?
And by the way, one of the problems in the practice test had a wrong answer. The problem which Kirchhoff rules, this problem number 21, the correct answer that we got was 0.45 rather than whatever. So problem 21, the answer that is correct is 0.45 watts. So do those, so you're definitely going to have one Kirchhoff rule problem, which practically what you have to learn is how to write the system of equations correctly. The solution, if you're comfortable doing algebra, do it. Otherwise, well, it's not going to be difficult. But you're definitely going to have problems similar to problem number 21, for example. It's not going to be the same problem. At least, well, we're going to have different versions. Okay. So problem number 10, you said, right?
Yes, please.
Okay, so problem number 10 from the practice test says that you have a helium nucleus between the plates of a parallel plate capacitor with given mass. What magnitude of the electric field is needed to make this?
That's number 11.
Oh, this is 11. Oh, okay. Yeah, you're right. I'm sorry. Yeah. Oh, didn't we do this problem number 10?
No, there was one like it on the homework, but when I was trying to figure out this one.
Oh, maybe the answer is wrong. Who knows? Maybe the answer is wrong. Okay, problem number 10 from the practice test. A simple circuit with 1 microfarad capacitor and 3000 ohm resistor, 6-volt battery, and open switch. Initially uncharged. How long after the switch is closed the voltage reaches 3.8 volts? Well, I don't know. Let's see. So problem number 10 from the practice test. So you have the capacitor of 1 micro. So here it is, C equal to 1 microfarad, and a resistor of R equals to 3000 ohms, and the battery that gives you voltage V equal to 6, right? 6 volts. So look, here's the switch. You close the switch, the battery, the capacitor starts charging. And it charges according to this expression. The charge as a function of time is equal to the maximum charge times 1 minus e to negative t over RC. Right, this is the expression. Well, so to figure that out, let's see what should be the maximum voltage. Well, so they want, so we don't, okay. voltage across the capacitor. We have the charge, but they're asking for the voltage, right? So keep in mind that charge and voltage are connected. So charge is capacitance times voltage. So if the voltage is 3 point something, the amount of charge is the capacitance times 3 point something. So you know now what charge you want to have on the plates of the capacitor. So what would be the maximum? What would be the maximum voltage across the plates of this capacitor? Is well, the maximum voltage and the maximum charge also. What would be the maximum value? Well, let's figure that out. So Q naught is going to be capacitance times, well, let's change the name of this voltage V naught so that, and therefore we have V naught. So is that right or not? So when you close the circuit, you're going to have some current flowing. The value of the current. Well, let's. I think that this is a good thing. So once you know this, you just have to solve the rest. What else do you need? You need the product of capacitance times resistance, which you can do easily, and that's it. So now, if you have the value of Q and if you have the value of Q naught, the expression is going to look like this: Q divided by Q naught is equal to 1 minus e to negative t over RC. And after that, this 1 to the other side of the equation, you get Q divided by Q naught minus 1 is equal to negative e to negative t over RC. And multiplying both sides by minus 1 is going to give you 1 minus Q over Q naught is equal to the exponent. And now taking logarithm, natural logarithm of both sides, is going to give you natural logarithm of 1. Actually, Q divided by Q naught probably can be simplified, right? Q divided by Q naught. So when you divide those two, C cancels and you have V divided by V naught. In other words, the value of this expression becomes V was 3.8. 3.8 divided by 6, right? So you have the value of this number, 3.8. So when you take the logarithm, so what is this number? 3.8 divided by 6 is what?
0.63.
0.63. So you have, so this is 1 minus 0.63 is 0.37. So logarithm of 0.37. Wait a second, the minus sign. Yeah, is equal logarithm of 0.37. So this is 0.37 according to. So logarithm of 0.37 should be logarithm of exponent is the power of the exponent. So it is negative t over RC. And therefore, the time is equal to negative RC logarithm of 0.37. Well, this is what we get. So I hope that it is the answer, but again, the answers are not checked. You have the opportunity actually now to check the answer. So what do you get?
Yeah, use that answer.
Okay.
0.003.
Okay. So the answer is E, right? Okay. So there were multiple steps here that you have to think a little bit before making them. But this is the process. This is the way. Okay, other questions? Other questions?
Thank you.
So, welcome. In the other section, people asked me about other problems from the practice test. But if you have done them, we don't, or you may have not looked at them. I don't know. Are you ready for the test on Friday?
I don't know about that.
Wow.
I'm definitely scared.
Wow. Well, yeah.
I have a question like about the test,
Yes.
just to clarify, if we cannot make it on Friday at 11, can we still come in at 1 to take the test in person? Okay, just making sure that was still. Can we do, so on chapter, I think 18, problem number 13 in the homework, you said would be most likely be on the test. Can we do something?
Chapter 18.
Yes.
Chapter 18.
I think
Yeah, it
it's
was
this, I
chapter
think it's
18.
the same equation right here.
Which one?
What?
I think it's the same equation for chapter number 13.
I don't think so. No, so chapter 18, number 13.
While you're looking at that, or someone asked how long the time frame for the test is.
50 minutes, but it is going to be doable in
Oh, yeah.
about 20 minutes. People that are online are going to have 55 minutes. People that are in person may stay for 60, 65 minutes, 70 minutes maybe. Julie, which problem was it?
So number 13 on chapter 18.
Okay, here is problem number 13 on chapter 18. 4 charges with the same magnitude on the corners of a square with given side. The 3 positive, 1 negative. What is the electric field at the center? So this question is making sure that you know how to work with vectors, because the electric field is a vector. So here it is, problem number 13, chapter 18. So here is the square right here, and they say the same magnitude of the charge, but three of them positive, let's say plus, 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 and let's say this one is negative. All of them with magnitude Q. And they ask the electric field at the center. The center of the square is the place where the diagonals intersect. So this is the point of interest right here, this point. And look, the way to think about this is by the electric fields created by pair of charges. For example, if you look at this charge, it is positive. The electric field created by this charge at that position is going to be this way. So maybe let's number those. So call this Q1, call this Q2, call this Q3, call this Q4, but keep in mind that Q4 is negative. So the electric field generated by Q2 is this way, call it E2. The electric field created by Q3 at the same spot is going to be exactly in opposite direction, because the rule is that the electric fields point away from the positive into the negative or infinities. So in other words, the electric field generated by this and by this cancel out. No electric fields created by them. On the other hand, the electric field by Q1 points this way, call it E1. And the electric field of Q4 points in the same direction. And it has exactly the same magnitude. So practically, you have to figure out the electric field E1 and double it, and you're done. The electric field created by a single charge is equal to the coefficient of proportionality times the value of the charge in magnitude divided by the distance between the charge and the point of interest. Well, that distance R is half of the diagonal. So distance R is right here, half of the diagonal. And look, you're given that this side, the side of the square is A. The diagonals of a square are perpendicular to each other and also equal to each other, which means that this side of the triangle that is formed is also R. And the Pythagorean theorem says that R squared plus R squared is equal to the hypotenuse A. In other words, 2 times R squared is equal to A squared, or R squared just by itself is equal to 2 times A squared, where A is the length of the side in meters, So you have to convert the number. For me, that is, for me, it is 4.1 centimeters. You have to convert it into meters.
Would it be A over 2 squared?
Oh, yes, of course it will be. Yes, thank you. R squared is A squared divided by 2, but divided by 2, no square roots there. And that's it. So your answer is going to be E total is going to be 2 times E1. In other words, it is going to be 2 times KQ in magnitude divided by R squared is A squared divided by 2. So this is going to give you 4 K Q divided by A squared, where A is in meters again. So, well, just keep in mind that it is going to, in meters, A in meters is going to be 0.041. When you square it, you're going to get more zeros than you want to see. K is the standard constant of proportionality, 10 to the 9th, 9 times 10 to the 9th approximately, but you don't round too much the numbers so that not to encounter surprises. Okay, yes.
How come A isn't R? Because it says that it's 4.1 centimeters on the side.
So they say that the side of the square is 4.1, right? But the point of interest is here. In the formula for electric field, you have the distance between the source and the point of interest. You have this distance, right? So
So shouldn't that be the A value if R is 4.1 and it's on the side?
so the value of R is going to be square root of this. So R itself is going to be equal to square root of this is A divided by square root of 2. So I kind of couldn't understand what exactly.
R is from the center to the corner.
This is R, right? This is R. This distance. Distance between the source and the point of interest. Is this okay or not? Okay, if you were asked to find the electric field, you do this. This gives you the magnitude of the electric field. You can say the electric field vector is going to point along the diagonal in direction to the negative charge. If you are asked to find the voltage at the same point, the voltage is a scalar quantity. So the voltage is going to be the voltage generated by this, this, and this. The negative charge is going to generate negative voltage. The positive charge is positive voltage. So maybe this, and you cancel with one of them, and the voltage created, let's say, by the first charge is just going to be K times Q together with its algebraic sign divided by R rather than R squared, where R again is this. And so the total voltage is going to be 2 times KQ divided by R. One of the negative charges creates negative voltage canceled out by the one of the positive charges, doesn't matter which one. Only 2 uncancelled positive charges remain, and the total voltage, of course, is double.
So if we didn't have the negative charge there, then it would be, we'd have 3.
Yes, if you didn't have the negative charge for the voltage, you would have 3.
Does it matter? So if Q1 and Q3 were different in how charged they were, like one was.
Well, so it doesn't matter which one is going to be negative. The answer for the magnitude of the total of the electric field is going to be the same, but the electric field vector is going to point in direction to the negative charge along the diagonal again. Yeah, go ahead and ask.
I'm not sure. So if, like, looking for the voltage, if Q1 was different than Q3 and Q2 in that it had more charge,
Oh, you just have to add them. So V total is going to be, so V total is going to be the voltage from the first plus the voltage of the second plus the voltage of the third plus the voltage of the fourth. And each of the voltages you calculate by this formula, keeping the algebraic sign of the charge. The voltages are easy because no direction, they just add up as numbers. The electric fields, you have to pay attention to the direction of the electric field because you don't add vectors just by adding their magnitudes. Okay. Other questions? No other questions? Look, I don't want to start the next chapter because I couldn't start it in the first section of the class. They just had many questions. And of course, the students in this class are better students, so they have done, you guys, you have done all the problems.
From chapter 19, can we do number 10?
Chapter 19, problem number 10. Let's see.
This one will also be on test, right?
Well, I don't know. I have to write the test, which is going to happen tomorrow, most likely evening. Problem number 10, you said?
Right. Unless I have it written down.
This one?
Oh, that one's on, isn't a practice one like that on the?
Yeah, a similar one was on the practice test, right?
I should have it written down right.
Not much different than this one. Yeah. Okay.
So I have one written down. I don't have anything with it, but I remember it had like a diagram.
Let me see.
Like a diagram of this. You had to solve. I think this is on chapter 18.
You have the laptop for chapter 18.
Chapter 19 as well.
Look at the screen and see if you're going to see this problem. So here is look at the problem from the screen. If you see it,
Okay.
She's been doing this like pretty much like up until now. Just like we're all 3/4 there. So she's top testing. We got a system. We got to do something. It's like, what do you guys do? How you guys want to do this class? So sure. So we'll see how it goes.
not this one.
We have that class together.
So it looks like this
I
one.
want to use it because I'm trying to do that. and it always says, like,
Right. The difference is that
definitely
there's-
so, like,
Primary food on conceptual.
I definitely for it.
Yeah. Is not the conceptual, but the quiz questions.
Oh, quiz questions. Which chapter?
It would have been chapter 19, so it has this on chapter 19.
Chapter 18 quiz question.
Chapter 19,
Oh, 19.
sorry.
Let's go over those. If you see it, just let me know.
Okay. Right there,
Okay.
this lovely one.
What is the electric potential at point A? So they have two charges with equal magnitude but opposite algebraic sign. And therefore, here it is. So I just, so this is quiz for chapter 19. And it is one of the slides. So this is slide number 9, page number 9 from the quiz on chapter 19. And look, they're asking about the voltage at point A. The voltage at point A is created by the red, and the value of the voltage created by the red one is this, where Q1 is 50. So this is equal to K times 50 times 10 to the negative 6 divided by the distance between the source and the point of interest is 0.3 meters. So this is the voltage created by the red one. The voltage created by the green one is K times Q, but this is a negative, so this, if this is Q1, this is Q2. Now, change the distance R1 to the first and the distance R2 for the second. So it is K times negative 50 microcoulombs divided by the distance between the source and the point of interest, which in our case is 0.6. So the total voltage is a sum, V1 plus V2. So you have to add those two numbers, and you probably can simplify them quite well. So you're going, if you factor out the common factors, so V total is going to come out to be some, let's see. Well, just do the arithmetic. So you're going to have something like K times 50 times 10 to the negative 6. And in the brackets, you're going to have 1 divided by 0.3 minus 1 divided by 0.6. So, well, it is arithmetic. Hold on, there is a name. Yeah, that's it. Yeah. Yeah, you have to do the arithmetic here. Oh, they just ask in this case, they just want to figure out if it is a positive or negative voltage. So which one is going to win? Here you divide by 0.3. Here you divide by a larger number. So this one is smaller in magnitude, and therefore the red one is going to win. The positive is going to win. Right? But you can even calculate it up to a number if you want. So the total voltage is going to be positive some number. Right? This is. Is it okay or not quite? Okay, other questions? Look, let me do a question from MCAT. So here is a question from MCAT. And if you insist, I can put it on the test. Here is a question from MCAT. So you are given a circuit And unfortunately, people that are online cannot see the circuit, but I'll draw it on the board. So you have a battery, you have one resistor right here. You have a system of 3 resistors here, and that system looks like this. You have one, you have a second one, and you have a third one, this. And they're like connected like this. You have, and you close the circuit to another resistor here. So let's put the numerical values of voltages. Well, voltages are not given, but let's see. So you have 1 ohm here. You have 2, 1, and 4 ohms. 2, 1, and 4 ohms in this combination. And you have 1 ohm here. They say that the voltage across the 4 ohm resistor, so this means the voltage here is V, call it V1, equal to 8 volts. And they're asking us to figure out the value of the current through this resistor right here. So they're asking about the value of this current. Well, is it going to flow in this direction or in this direction? Nobody cares. Yes.
So yesterday during the problem solving session, we did something similar to this. And I guess my question just is, when it talks about the voltage drop across the resistor D, is that same voltage? Is that going to be the same voltage drop for resistance C and D?
Exactly. Yes.
So between points A and B on that.
So this voltage drop here is the same as the voltage drop here, and the same as the voltage drop here, and the same as the voltage drop here. Just because all of those points are connected with wires, and the potential doesn't change when you go along the wire. So the voltage drop of 8 volts is also here. Right? That's, and once you know that, the rest shouldn't be. So you can do it in different ways, but in MCAT type of questions, the time is what matters. So you have to try to do it as fast as possible, and you can do it in, well, to do it according to the rules, find the effective resistance of this combination. What is that effective resistance? Well, the inverse of that effective resistance is equal to the sum of the inverse of 2 and inverse of 1 and inverse of 4. So 1 plus 1/2 plus 1/4 is 1 3/4, right? In other words, it is 7/4, but this is 7/4 is the inverse of the resistance. So the resistance of that combination in the circle has to be 4/7 ohms. And now the things are not difficult now, because you have, this is one resistor with value of 4/7. Voltage across that resistor is 8. The current that falls in that combination is going to be voltage divided by resistance. Voltage, we called it V1, but doesn't matter. So it is 8 divided by 4/7, which is 14 amperes. So the current that flows, that enters this combination is 14. but it is the same current here and here, right? It is the same current. So the current I everywhere here is going to be, well, when you replace this combination of resistors with a single resistor, you have a circuit with all resistors connected in series, and the current in this entire circuit is always is the same, 14. Yes.
So the voltage will change throughout the circuit, but current will always be the same throughout the circuit.
Well, so look, this circuit now looks, after you replace that combination, looks like this. This is 4/7 ohm. And this is again 1 ohm. And here is the battery. So now in this circuit, you have everywhere the same current, and it is 14, the same current. But the voltage here is 8. You can calculate the voltage here. Current is 14 times 1, so it is going to be 14 volts. And the same thing here, 14 amps times 1, again, 14 volts, which means that the battery has to be how much? 14 and 14, 28 and 8, 36.
Then current will always be the same within a branch of the circuit.
So the current is the same here, but once it reaches this junction point, it is going to split into 3 branches with different values, right? So the current is the same up until it reaches this junction point. Okay.
And you can put that one on the test.
Yeah, but the first section doesn't know. Oh, but I can. You guys different versions. We'll see. So count on this, but I may ask a different question, right? I may ask. But what can I ask here? Anything that comes to your mind, right? Yes.
Does the A underneath the figure represent the answer? Because if that's the case, then it would be, oh, it's multiple answers. I understand now. I thought A just stood for answer.
No, I make mistakes, so that's perfectly fine too. Okay, yes.
Sorry if I'm getting confused here, but the current is the same as the voltage in this case, just because it's 1 ohm. So if you were to look at the equation, it'd be I equals the voltage, which is 14, over the resistance of that resistor, which is 1, which is how you find the resistance across RE. So the question asked, what is the current across RE? So the very bottom one.
Yeah, what is the current across here? The current is exactly the same as it was here and here also. This, and it is 14, right?
Okay.
So practically, you can they can ask what is the current here or here and here, and you can figure it out immediately without calculations, because voltage is something. The current here is going to be 8 divided by 2, 4, right? So the current here is going to be 4. The current here is going to be 8. So 4 amperes here, 8 amperes here, and 8 divided by 4, 2 amperes here. If you add them up 2 plus 8 plus 4 gives you 14 when they get together. So it is pretty much like plumbing, right? This type of, well, slightly different, but Ohm's law solves all of those questions. Okay, if you don't have other questions, let me ask you about this circuit right here. This circuit right here. Let me draw it on the board and see how this circuit is going to react. So consider the following circuit. One light bulb, a second light bulb, and maybe a third one light bulb right here. All of them are equal, even though, and connected to the grid. So here is the 120 volts RMS value, and you have a switch located right here like this. The first question is, when the switch is open, how many light bulbs are going to be on? How many? When the switch is open. Let's see. So when the switch is open, you can completely forget about this horizontal, this vertical line with the switch. And you're going to have 3 light bulbs connected in series, right? And therefore, all of them are going to light up. And how many volts are across each light bulb if the light bulbs are identical? So 120 equally divided between the 3, 40 volts across each of the light bulbs. Now, if I close the switch, what is going to happen? If I close the switch, here it is, I close the switch. The last one is not going to exist anymore, right? It's not going to have any voltage across it, and only the other 2 are going to be on. Yes.
Does it still have voltage going across it? There's just not enough to turn it on?
No, there is 0 voltage across it because look, once you close the switch, this point is connected to this point, and therefore those 2 points are under the same voltage. No voltage difference between them. No voltage difference between the two ends. You need a voltage difference across a device in order this device to be on. And here, nothing. So there is no voltage difference between this and this point. No current can flow. Right? Only the other two, look, the voltage here is the same as the voltage here, like here, but the voltage here is different on the other end here because, so you have it could be confusing. Yes.
So because that third light bulb is off, the 120 volts gets equally distributed between the 2
That's
that are
correct,
on.
yes. So 60 volts across each of the 2 light bulbs that are on. And you see that 60 volts means brighter light bulb, right? But when you distribute along the 3 and you have only 40 volts across each of them, they're kind of dim and you have much brighter light when you have higher voltage across each of the light bulbs. Well, next time we're going to, well, after the test, we're going to play around with magnets next time. So this is next week. Okay, last chance to ask questions at
I'm just confused still why, like, because in this situation, does it, does the current not pass through the last one because it'll just take the shortest, easiest route to go back?
That's correct. So look,
There's nothing happening in the loop farthest to the right when it's closed because the current just wants to go back to the.
yeah, the current is only going to flow this way. The current is not it doesn't want to go this way. All right. Well, so this is misleading if you think in terms of water flowing through hoses. But you have to, again, this is electric current and you have to think in terms of potential difference. In order the light bulb to be on, there should be a voltage difference between those 2 points. And since those 2 points are connected with a piece of metal, they're under the same voltage. That voltage may not be 0, but it is the same here and here, and therefore the current doesn't know should it flow this way or the other way. Doesn't matter. It cannot flow anywhere.
I guess I was just confused because technically those 2 points are still connected with the big outer loop.
Yeah, they are connected, but those 2 are the same at the same voltage. So think about as if you have somebody pushing this way and somebody pushing exactly in opposite direction. No voltage difference. That's it. No potential difference between those 2 points. And again, I'm giving you this example because just you to struggle with the questions that you're struggling right now. This is the way to understand it. So, sweet. So those things